All right, so I'm going to start with the later section first because that's really the precursor to the stuff we're doing later on. And we're going to start solving something. Again, I know you're going to do this, or you did this in Calc 2 because this is the first half of my lecture on Monday in Calc 2. And that is to solve what are called separable differential equations. Now, separable differential equations have several different forms, and so I want to go through every possible look you can have because it's really a matter of convenience. It's kind of like saying, do I define my function as y equals or do I define it as f of x equals? Because that will determine the derivative notation I'm going to use later. Well, a separable differential equation, and I'll stick with x and y right now, being independent and dependent. It really doesn't matter, right? It doesn't matter, but sometimes there's ambiguity and you might think you're doing the wrong thing just because you're looking at something slightly unfamiliar. So a typical separable differential equation will be something of the form, sorry, I'll write it like this. This would be kind of a generic form. It's not the only form, but it's kind of generic. And that there's a function of x and a function of y that are separated. Now, can I combine them? Can I move things to either side? Yes, but the only way they can be combined is either as a product or as a quotient. That is huge, because if I combine them as a sum, it's a very different and probably much harder problem. But if it's in this form, I can manipulate this, okay? So I'm going to go back and remind us of some things. And I reviewed integration by substitution today in my Calc 2, and I was surprised at how many people were not really certain that was what they were supposed to be doing. Well, when I'm solving a problem like this, my dependent variable is y, my independent variable is x, so any integration has to be done with respect to x. But what does that mean when I do this? This is always a point of confusion for people. Do I cancel the x's?
If you're a physicist, yes.
Well, if dy dx was a quotient, then I could, but dy dx is one thing. It's a function. Dy dx is not a quotient. It's a function, and I'm integrating with respect to x. But the problem is there are no x's in the statement. There would only be y's. So this is equal to the integral dx. How do I know that? Because what's the antiderivative of dy dx? Isn't it just y?
Yeah.
So what's the antiderivative of, I'm sorry, I wrote dx, sorry. What's the antiderivative of dy?
Y.
Y. In other words, I'm getting the same antiderivative. You're not canceling, you're integrating this with respect to x, but there are no x's in the statement, there are only y's. This is the primary basis of u substitution. This is why people struggle, because I'll see people do weird algebra. They'll make dy and dx as quantities or quotients, and they'll divide and they'll multiply, and I'll get all sorts of crazy stuff. I'll have functions divided by dx, just, like I said, just everything's going out of whack. Dogs sleeping with cats, just everything. It's crazy. But I have to remember that that's the rule when I'm doing this, because I want to break this apart. It's called separable because I literally separated into two problems. So what I want to do is have the y's go with this one and have the x's literally on the other side. Now, don't worry about what Q and P actually look like. Q might be something simple and its reciprocal might be something simple and vice versa. But if I rewrite this, one way I could rewrite it would be like this. Do you agree? So I'm assuming it's not zero. Is this useful yet? Not yet. I want the Q to go with here, and here's why. We're going to do enough of these that this will be actually quite simple. And I said, don't worry about the specific functions or what their antiderivatives look like. I just am interested in setting it up. Now that I have this, now I'm going to integrate both sides with respect to x, which makes this one now 1 over q of y dy, which will now be entirely a function of y when integrated. This is going to be something purely of x when integrated. Are you with me so far? The order and where I put things is not really relevant, but when I integrate, I've got to integrate the y's with y's and the x's with x's. There's no gray area there. So let's do a simple example right off the bat. before we start getting into all the alternate forms of this stuff. So let's suppose we have something of the form, how about e to the x dy dx equals, how about, I don't know, the secant of y. Now, when I say solve this, what are we actually asking for, probably?
I think with dy dx.
Well, what do you think I want my answer to look like?
Y equals something?
Yeah, if I can. Well, I'll just say if I can. If I can, I'd like it to look like y equals. It may be that when I'm done integrating, what I have might be the equation of a circle. Right now, so I'm not going to worry about solving for y. But if I can solve for y, I write y equals. If I can't, but I can solve for x, I might choose to write x equals. I'm going to show you there's actually 3 viable forms for every problem, depending on what it is you're using it for. When I'm all done with this one, I can probably solve for y. So I need to rearrange it like we did before.
What was the right-hand side again? It was.
That's secant y.
Okay, thank you.
Okay, so if I manipulate and I move things around, because I really need this to go over here and I need that to go over here, what's the reciprocal of the secant?
Cosine.
So I'm going to have cosine y dy dx equals what?
1 over
How about,
To e to the negative.
Oh,
how
yeah.
about e to the negative? Yeah, it might be a little bit cleaner.
Yeah.
Now when I integrate both sides with respect to x, I'm just going to go right to the final form. Is it correct for me to say this? Stare at that for a moment. Are you okay with that now? I'm integrating both sides with respect to x.
No.
So dy dx integrated with respect to x is the integral of dy, so yeah. Now, does that look scary and intimidating?
No.
No, rarely will these be something that's terribly taxing. You're usually going to have something that you're not going to struggle. But when you look at this question, you don't see that one. You have to manipulate it. You've got to rearrange it in such a way. I cannot do cosine y with a dx. That's not mathematically possible because y is technically dependent on x. So x and y cannot be in the integral at the same time. They can only do that if they're independent variables, and they're not. How do I know they're not independent variables? Because that's an ordinary derivative, not a partial. That's the easiest way to tell. Now, can I finish this?
Yeah.
Yeah. So, left side,
Sine of
and
1.
be very careful you're not losing variables. What's the right side?
Negative e to the negative x.
What about the plus c?
You need 1 plus, we need just 1 plus c.
Just-
Yeah, here's the danger. Plus c, they're going to cancel. Could I say plus c1, plus c2, and then throw the c1 over and call that c3? Yeah, so why not just do it once? Remember when you first learned integration and you're integrating polynomials, you learned that the integral of a sum is the sum of the integrals, so you integrated one term at a time. So I give you a third degree polynomial. You have an x cubed, an x squared, an x, and a constant. You did not put plus c1, plus c2, plus c3, plus c4, and then add them all up. You put one c at the end. There's always only one c. You never have to do more than one c in one integral. So just do it at the end. Does it matter which side the c shows up on?
No.
No. Now, everything I said is true and correct. Is this a good form of a final answer?
No.
I could do better. What if I just added the e to both sides? Turns out this is an absolutely acceptable form. Might not be the most useful form, but it is acceptable. Putting both variables on the same side and throwing the constant on the other, or putting everything on the same side and having it equal 0 is absolutely correct. But, now, again, most of you have been in my classes before and you've probably heard me say this. At this point, it has nothing to do with being right or wrong. It's what is the most useful form of your answer. You're in a situation where whatever answer you get, you now have to use later in the problem. Maybe you have to use it 2 or 3 times. Maybe you're going to substitute later on. That's probably not the most useful form. The most useful form probably would be isolating one of the variables. It really doesn't matter, except that the way the question was stated, y is clearly the dependent variable, so therefore solving for y makes sense. if I can, if it's convenient, if it's not too taxing. I think in this case, it's not that taxing. So what is a better answer, probably?
Y equals the arc sine of
Inverse sign.
inverse
Yeah, inverse sign.
negative.
Yeah, get used to that one, because arc is not inverse, by the way, regardless of what somebody told you. Principal arc sine is inverse, and it's actually a different notation, capital A. By the way, I was lucky enough to learn that really early, and I had classes where instructors would mark people completely wrong and not tell them why. Yeah, you try using arc in an upper division class, you're gonna get no grace whatsoever. No, inverse sign. The only reason people use arc was because for decades,
It was related.
there was no way to know. There was no way to do the exponent when you were writing. This was before word processors came out. Nobody used arc. Nobody in math and science ever uses arc, because arc is not unique. If I said, what is the square root of 9? What's the answer? 3. It's not a trick question. What are the square roots of 9? Negative 3 and 3. What are the fourth roots of 1? Plus or minus 1, plus or minus I. You guys learned this in pre-calculus. Oh, the answers are not unique. The principal fourth root is 1. What we often do is we just automatically say that. Did you know natural log produces an infinite number of answers to every question? But we always are assuming you mean the principal natural log. Yeah, it's not a unique solution. Go back to Euler's formula. Aren't there an infinite number of representations of every point on a circle when using trig? Oh, I forgot about that part. Yeah, you have the 2k pi thing. Like, yeah, I'm going to stay away from that, but that will come up in this class. If there's a situation where it clearly is a unique answer we're looking for, the word is principal. We often just assume it because it's not practical. You know, so when I say, well, what's the square root of 9? Well, which one do you want? No, I want the principal square root because I asked it singularly. But the moment I put plural, you know I mean all solutions, right? What are the solutions of sine equals 0? Well, the answer would be k pi. For every integer k pi would be the answer, wouldn't it? I said solutions. And so what do we often do? What are the solutions between 0 and pi, or something like that, between 0 and 2 pi? This is a great answer. What about C? Can I do anything with that?
Can you?
I can if
Can you impose like a initial condition?
I gave you an initial condition. I don't come up with one later, but if I gave you an initial condition, so I want to go back to that one. By the way, could I solve for x in this statement?
Yes.
Absolutely. And depending on how I'm using it later on in the problem, that might actually be the best answer. But I don't know how this is going to be used. So I'm probably better with one of these two. Now, let's go back to the beginning of the problem. What if I said that y of 0 equals, I don't know, y of 0 equals 2, or something like that out there. Well, actually, let's not use 2. Let's do, yeah, y of 0 equals, that's ugly enough. We'll do that. Y of 0 equals 2. I just gave an initial condition. When x is 0, y is 2. Where do I plug it into the answer?
X would be, I mean, you're just plugging 0.
Where in the process? Well, first of all, the answer is yes.
Once you have your answer.
Once we've done.
Okay, my preference is probably as soon as you can. Now here's the reason why. I don't like carrying the C all the way through and then trying to figure it out at the end, because I think it's too much thinking here. Because what if C ended up being 0?
Oh.
Is that a possibility that the C could be 0? Wouldn't you want to find that out at the beginning rather than carrying it all the way through? Yeah, so because C could technically be 0, I'd rather find it in the first step that I can find it in. Plus, this looks a little bit too scary to try to figure out what it is there. So I probably would put it over here. This is the first chance I had. So now I have what? Sine of 2 equals negative e to the 0 plus c. What's that?
1. Oh, wait, negative 1.
Negative 1 plus c, therefore what's c equal to?
Sine 2 plus 1.
Sine.
Sine 2 plus 1?
Yeah.
And now I put it in right there. Because I'm now done, I don't need it anymore. But I think, I don't want to try to figure it out here, because I just think that's, You all agree that it looks a little bit scary to try to work backwards and do the algebra here. So an initial condition just means you're finding a C. There's no plus C in your answer, there's a constant, and the C technically could end up being 0. You have no control over that, you're just trying to discover it. Now, this is one form, but it's not actually the most common form, strangely enough. The most common form is kind of goofy looking. Oops. Well, that's strange. This was a new, hold on, this was a new pen. Oh, here's it. Okay. How about, let's do something simple here, like, that's an S. Y squared dx plus cosecant dy equals 0. Now, that just looks crazy. What's the independent variable in this case?
Law.
Anything.
Yeah, I like that answer. I'm not clear, so actually it could be whichever one I want it to be. Oh, but only one of them can be independent. How do I know? Again, straight D's. So one of them has to be independent. You actually like this form better. Because right now it doesn't matter which one's the independent. It's sort of like what's more convenient, but also you're really one step closer to being able to integrate. All I got to do in this case is throw 1 on the other side, and I'd have y squared dx equals negative cosecant x dy. And now what do I want to do with these guys?
Divide.
Swap them out. You with me so far? So if I rewrite this, what will I have?
1 over cosecant x dx.
Yeah, but better than that. How about negative sine x dx equals
1 over y squared.
1 over y squared. Now that one, because I'm going to integrate, I probably want to write that one that way. You know, make my integration a little bit simpler. You like that so far?
Mm-hmm.
Everybody okay with that? You notice I did not move the dx and the dy. They are not quantities. I can't tell you how many times I've seen, but let me divide both sides by the dy and the dx, and then they end up in a denominator. It doesn't have any meaning mathematically. They're instructions, they're not quantities. They tell me I'm going to integrate with respect to this variable, but I have to have the same variable. This would have been fine if both variables were independent. It wouldn't be easy, it wouldn't even be all that useful, but it wouldn't have been incorrect. But because only one of them can be independent, I need to do it this way. Now, last step before I do some calculus. That's it. That's all I got to do now. Now we integrate. I was going to get retired. So when I integrate this, what do I have on this side?
Cosine x
Positive cos x?
Yeah.
and
Negative y
Negative.
to the negative.
Yeah, so I'm going to write negative 1 over y plus c.
don't forget the
I can solve for y. It'd be kind of ugly looking. I can solve for x. It might even be uglier looking. Or I can throw them both on the same side. Again, all three are correct. In fact, in this case, if you want to be lazy, what are you going to do?
But,
Throw them on the same side.
The initial strategy, though, for this is if you were given an initial condition, then you would want y on one side to solve for c.
Well, actually, if I gave you an initial condition, I would just go ahead and do it right now.
So as soon as you're done integrating, then you would just throw
I do it as soon as I can because it's usually the least taxing algebra. Because if I do it now, it's going to be constant c. But that's not the case over here, is it? I have function of constant plus c, and I got to work backwards, and I don't want to do it here. You can't. I don't want to do it here. It's icky. That's what I'm saying. It does not matter when you do it, but I think doing it sooner always makes things easier. Always. I can't imagine a scenario where that makes it harder.
What's the idea of dividing both sides?
Well, because I need the same, these are not the same variables, so this cannot be done as stated.
Oh, gotcha.
Yeah, so I need x dx, I need y dy, so I just multiplied both sides by their reciprocals. That's actually not that taxing. What you're going to find in every textbook is the nature of the problems at this point are usually with rare exceptions, they're usually going to produce really low-level integration problems. They're not going to be things that require techniques. Okay. Now, I asked this question last day in Calc 3. How many trig substitutions did you do to integrate? Probably none. Okay. How many partial fractions decompositions did you do in order to integrate?
4.
4? I probably none. I've taught each calculus course. Well, between the three, I'm up well over 150, probably closer to 200 times. How many integration by parts did you do? I think I actually will do a problem and say, as we set it up, this will require integration by parts to finish. I think I actually did that once. And then we moved on. So I'm pretty sure that I've never done any integration technique other than a simple U sub in a Calc 3 class, ever. Of all those ones you learned in Calc 2, there's only 2 that you're ever going to use again. Parts and partial fractions decomposition, and that won't even be for integration, that'll be for something else. When we get to Laplace transforms, it'll just make your life easier if you remember, and we will review it. Parts comes up whether you want it to or not. There's no way to avoid it, just simply because we mix things together. We have x times sine occasionally. You know, we occasionally will mix the x's, the sines, the e to the x's. We don't get to the obscure stuff. Parts will come up occasionally, not a lot. It will come up occasionally, but not really any of the other ones. As long as you know your basic antiderivatives without thinking. You see, what do I mean by basic without thinking? I mean basic without thinking. I'm not going to ask how many people were fully ready to put a negative sign here, right? But that can happen, right? A little bit of rust. No, we've got to be able to do that. We've got to be able to do that one. Because those are not taxing. There are enough that are hard to remember, but not those guys. Those really shouldn't bother us. So a separable differential equation simply means the x and y terms can be connected either by a product or by a quotient, but not by a sum. So aren't I adding these? No, I'm not adding these. If I move this over to the other side, wouldn't this be y squared times the sine function? If I move it, not y squared plus the sine function, times. So products and quotients, because a quotient is a product of a reciprocal, there's no difference. So if we went back here and I had e to the x plus secant y times this, that's a much different problem. That is a much harder problem. In fact, that may be beyond our skill. Okay, so we start with this one. It's considered the first one. I don't want to say it's easy. It's just the first technique we learn, and it's generally not considered very taxing. Chapter 2 in the book, which is where we are starting, 2.2, this is always the first one. And there is a hierarchy. As we learn a whole bunch of techniques over the next couple of weeks, when you're looking at something, it's just like, remember in Calc 1 when you saw a whole page of integrals? You're like, oh my God, they all look exactly the same. Your first goal was to classify them. Now, in Calc 2, when you had your methods of integration, you say, that one looks like a parts. I think that's going to be a trig sub. I think that's going to be a partial fraction. The moment you could classify it, then you knew what strategy you were going to use to solve it. Am I right? But if you couldn't classify it, you can't even start the process. Well, in this class, it's going to be, this looks like this type of differential equation. This looks like this type. And once I identify the type it is, I now automatically know the strategy. So the very first type is separable. And that will always be the first thing you look for because it is generally considered the least taxing. There are some that are very long. They're very involved. And, that you're stuck. But just like integration, occasionally you run into a problem where you have more than one technique that would work. I'll give you the most simple example of all, because I do it both ways, right? You have something like this. Can I do a trig sub here? By the way, there's no function that looks like that as an antiderivative. That requires technique. Could I do a trig sub? Yeah. I'd say let x equal a...
And x squared 2.
A sine.
Secant.
Secant, yes.
If it was a squared minus, then it would be sine. If it was a squared plus, then it would be tangent. Don't worry about that. But you say and then I would go through and it's very long and there's a lot of stuff. Could I factor that?
Yes.
And that's a one-step partial fractions decomposition, split it up, it's a couple of logs, put it together, piece of cake. Those are very different techniques. When I have a denominator that's a difference of squares, you could always do it either way. And I always tell people partial fractions is way, way, way simpler. But occasionally, you have a problem that can be done two ways. And does it matter which way you do it? No. Now, is it true that when you're integrating, sometimes you have more than one choice? If your answer has initial conditions, and we just talked about this a minute ago, This is an answer. This is not the answer because I can manipulate this. Heck, what if I decide to multiply both sides by negative sign? You know, because I want the y to be positive. If I wanted to solve for the y, I really do want this to be positive at some point. Are there versions of this answer that are correct and acceptable and perhaps even more useful? Yes. Does it matter which one I use? Not at all. And so why do I use those types of words? Okay, is there anyone here who hasn't had physics? Okay, so you're in a physics class, and I always have fun with this in calculus because you're doing the calculus problem, you got to the end, you got to integrate. I'm all done. I am completely done with the problem. Now that you've all had physics, you said, no, you just did the first step. Am I right? You did the first 10% of the problem by doing the integral. We're not even close to being done. There are so many more things involved, and this is why I say it in these terms. Whatever answer you got was right. But are you going to use that version, or is there another version that might be more useful? If I'm going to have to substitute in later and do other stuff, I probably want to isolate one of the variables that just makes it easier. If my answer is a natural log, but I'm going to put it in an exponent later, I might want to manipulate and use that fact. It's kind of some of the stuff we're going to look at today. The version of the answer you give should be designed to what is the most useful form of the answer based on what I'm going to do next. Not is my answer right or wrong. I'll just assume your answer is right. Okay? You've never had the experience, of course, where you did a problem, you got an answer, the back of the book had a completely different answer. That's never happened, right?
I mean, sometimes the book is wrong.
Do you all, well, let's assume the book is right. Do you always assume you're wrong?
No.
No. I can honestly say, no, not to brag, but I've never assumed I was wrong. And I don't assume the book is wrong. I assume the book is just a different representation of the exact same answer. And you know what's happened literally 99.9% of the time? It's exactly what it was. Most of us assume we did it wrong. I will use Wolfram. I love using Wolfram, but never to integrate. Anybody ever integrate with Wolfram? You always get 7 answers, 4 of them are complex, and you're trying to figure out how the heck you integrated e to the x. How do it'll give you usually 7 answers and 4 of them are complex, and most of them are not useful, and they'll give long explanations. You're going, all I wanted was an integral. No, never use it to integrate. Integrate the problem and then use it to differentiate your answer. And if you get back the original function, then you know you did it right. That's how you use Wolfram. Never do it in reverse. No, I can always get an answer by integration faster than Wolfram, and my answer is usually better. I created a table of integrals for the Calc 2. I'm not really doing the tables anymore. We've sort of evolved beyond that. But in every calculus book, there'll be a table of integrals. And there'll might be 100 of them, and only really 30 of them might have antiderivatives. All the rest of them give you recursive. The answer to this integral is just another integral that's more work and harder. It's actually an incorrect answer. Because the author didn't know what to do. It was an integration by parts problem, and they just kept going. No, I will do these problems, and I'll get an answer, and it'll be one ugly quotient. And I'll do it on Wolfram, and Wolfram will give me 4 different quotients. And then I'll just combine them into one, and it'll be my answer. I don't assume I did it wrong. I just assume I have an easier version of the exact same answer. But I'll use Wolfram to differentiate my answer. And if my answer's derivative isn't my original function, then I know I have an error, and then I can go back and fix it. And that's actually a better way to use Wolfram. I'm a big fan, but a lot of, see the problem with using Wolfram from integration, I would say 1/3 of the time I try to use Wolfram for integrating. And I don't know who wrote the program, it makes me laugh. I'll get something like, are you sure you want to ask this? I'll get some smart alecky response because the program cannot do it. I've already done it by hand with a pencil, no calculator. I did it in 30 seconds, but the program can't because the person who wrote the program didn't know how to do the problem. It was obscure. I didn't have any trouble doing the problem, but I just want to ensure that I did it correctly. So then I differentiate my answer. But Wolfram won't be able to do a significant number of the integrals. In my Calc 1 last semester, I had a student, he asked to sit in on a few classes. He'd had calculus years before, was going to have to take DiffEq. I actually thought it was going to be in this class, he's not. And he wanted to review some of the calculus. So he went and got a bunch of the old Calc 2 problems. And he came to me with a particular problem. He said, this was in the Calc 2 stuff. He goes, I don't know how to do this. I go, no, that's going to be, you're not going to be able to integrate that. That has no antiderivative. He goes, but the back of the book has an answer. And I just for fun, I went to Wolfram, got the answer, and Wolfram couldn't actually give an answer. It was beyond Wolfram's capabilities. And I started looking at it, and I said, what if we changed this thing in the problem to this thing, and then we got the easy answer in the back of the book? I say it was a typo. The author asked an impossible question. It was, instead of e to the x, it was like e to the x squared. When it was something, And I said, he goes, how in the world do you know? I said, I'm pretty sure a calculus book is not going to ask a question that our highest form of technology says I can't do. But the point is that every time you do a problem and you get an answer, you have to trust that your answer is correct, but you have to have a way of checking it. Now, we're going to do a problem. This is one of my favorite problems to do. If you were in my Calc, I do this in Calc 1. I don't know if I do it in Calc 2. Has anyone ever done the row your boat problem with me? You would know, because that's row your boat problem. Okay, here's the question. God, pens are killing me. All right. There are an infinite number of variations to this question, but we are all going to run into this problem, and I need you guys to be convinced that you're not wrong. It's hard to convince people that way. No, I didn't get what I was supposed to get. I did it wrong. No, you didn't. You just did it differently. And differently doesn't necessarily mean wrong. Sometimes differently is better. Now, this side of the class, you're the row your boat side. This class, you're the gently down the stream side. So row your boat people look at this and say, obviously, let u be sine x, and then the du is cos x dx, and okay. But the gently down the stream people go, no. Sine is just so boring. So what do you guys do? You say let u be cos x, duh. And then the du is negative sine x dx. So the row your boat people say, well, when I do this, then this just simply becomes the integral of u du, which is 1/2 u squared plus, I'll call it c1, which is 1/2 sine squared x plus, okay, duh. But the gently down the stream people, which kind of have a complex ending, the nose up in the air, they're like, no, we like to take the harder route. So they do this problem, and then they have clearly, I put that negative here, right? And so then we have negative u du, which is negative 1/2 u squared plus, call it c2. And so when I substitute in, I get negative 1/2 cos squared x plus c2. So the row your boat people who are like, duh, it's a 1/2 sine squared, and the gently down the stream people go, no, it's negative 1/2 cos squared, and then it's on, right? You guys like, what is it, what's the famous movie, where they stand there in the street getting ready to fight? There's a bunch of dancing.
West Side Story.
West Side Story, God, whatever. The Sharks and the
Jets.
And the Jets. I always love that. Right before the fight, everybody's doing perfect rhythm, doing that. And then they dance a fight. Yeah. So who's right? Because these answers are really not similar. In fact, in case we didn't notice, one of them is negative, and cos squared is not. So clearly there's a problem here. Or is there? Well, there's a Pythagorean identity relating sine squared and cos squared. What is it?
Sine squared.
Well, so I can replace sine squared with what?
1 minus cosine.
1 minus cos squared. And if I do that, I'm going to get 1/2 minus 1/2 cos squared x plus c1 plus 1/2. Well, why don't I just call that c2? Do I now have, oops, got too many equal signs, sorry. Equal, there. Yeah. Do we have the same answer?
Yes.
Yeah. Which one's better? Yes. Doesn't matter. But these answers don't even look similar. This is what all of you have faced, you should have faced at some point, where you did it, you thought you did it flawlessly, it's not even similar, I must have done it wrong. No, never say that. Unless you actually see an error in the process, say, no, I think I have a different version, let me check. Because maybe the version you have is the better version. If there is more than one correct version of an answer, you're never going to see multiple versions when you check. Right? Wolfram's the only one that gives you multiple, but a lot of them are not useful. So which one is the useful answer? I don't know. Where am I going to use it in the next step of the problem? Does that make sense? So get into the habit of when you're giving an answer, yeah, give the first answer that comes up, but say, is this useful because am I going to have to use this and substitute later? Or something as simple as, is this answer going to be easy to check through differentiation? You see, going back to here, God, I don't want to differentiate this. Do you want to differentiate this? But can I differentiate this? Yeah, but if I'm putting this back into the original, boy, I'd be hard pressed, So I would probably differentiate an earlier version of it. It's not so complicated. And again, all roads in that case are correct. Okay? Let us move on. This is separable. Now, the final answer to a separable, I just said, in general, it is considered that every problem has three perfectly good forms. Solve for y, solve for x, throw everything together. I really don't care. If I can solve for y seamlessly, I'm going to solve for y every time, because that's probably going to be the easiest one for me to check, and it's probably going to be the one I'm going to use later. But if this really is the end of the problem and it's an exercise, then don't sweat it. Now, there are some applications that we want to look at next. We are not going to solve these problems. So when I have these problems on a quiz, I'm going to ask you to state the differential equation. Half of you will state the differential equation. It'll take you about 10 seconds. The rest of you will go through and solve it from beginning to end and give me a couple pieces of paper. And you look at, oh, it's a 4-point problem. Boy, this really took a long time. It's like, no, don't solve it. That's in the future. I just want you to state the problem. See, not even, just state the integral. Don't solve the integral, just state it. So there's a few versions because we want to get into the habit of how do we correctly write a differential equation for an application problem. Because this class is not abstract, that we learn how to solve all of these methods abstractly. No, this class is all about application. It's 100%. Everything we do, we want to apply to a number or a problem. So let's start with the most basic one of all, and that's population growth. Now, in a very short time, I will ask you to solve some of these, but I think that doesn't come, hang on, I think that's beginning of chapter 3. Yeah, beginning of chapter 3 we do this. We have a couple of weeks before we actually are solving these. We just want to get in the habit of the correct statement. Now, population growth. Now, I always have fun with this one. In 1976, the world's population was 4 billion. So that means that January 1st at the stroke of midnight until December 31st at 11:59 p.m. and 59 seconds, the world's population was exactly 4 billion. Is that correct? Because that's what every book you've ever read, right? That's the kind of stuff they say. How long was the Earth's population 4 billion? For probably a split second. Yeah, we went right through it. At some point in 1976, the Earth's population hit 4 billion. I mean, we're probably close to 8 billion now. I don't know exactly. But every time you read anything on population, it makes me laugh. It'll say the world's population is. You're driving into San Diego from out of town and you see the sign, now entering San Diego, and it has 2 numbers on there. Elevation and population. You go, oh, when was that accurate, by the way?
Never.
Well, no, it was accurate for 5 minutes. When?
Makes
What
sense.
year is it? 2024? So when was it accurate?
2023.
In 2020 for a few minutes when the census was taken. For a few minutes. People have born, died since then. I have fun with that. Populations aren't, right? They're not static. They grow, but how do they grow? They grow exponentially, which we're going to prove later. I'm not going to go through the derivation. I will for that one. But populations grow exponentially. I've had many students over the years say, well, everyone tells us they grow exponentially. How come they don't grow linearly or some other way? And that's a great question. You're going to the bank later on today, and I found this account, but you get $100 a month interest. Think about that for a moment. You have an account, there's an account at my bank that gives $100 a month interest. Well, if I'm wise, what I'm going to do is I have $100 so I can break it up into 10,000 1-cent accounts, which I will do. It'll take a little while, and each one will earn $100. Is that how it works with money?
Uh-huh.
Do you get interest just straight up, or isn't it based on a percentage of what you put in? Isn't that how it works? Yeah, I'm pretty sure that's how it works. So if I'm putting money into an account, there's not a dollar amount, there's an interest rate that is applied to my principal. Populations, you don't say a certain town is growing 50 people per year. It doesn't work. What if there's only 2 people in the town? No, a town will grow 3% per year, perhaps. All populations of anything, even money growth, which is even separate, it's not exponential, that's what's called periodic growth, but everything is based on a percentage of what's currently there. Your rate of change has to be based on what's there. So if I call y of t is the population at time t. Now, I'm going to be really vague on purpose. Does this have to be people? Could this be, you remember, the bacteria in the petri dish, doubles every 4 hours, what's the population? It could be fish in the sea. I could be talking about an unstable element, and by the way, I'm talking about, some unstable element where time is not measured in years. Time might be measured in nanoseconds, right? So if I'm talking about people, probably what unit am I using for time? Probably.
Or year.
Seconds? No, probably year. You guys multiply really fast. If I'm talking about money, well, that's a tricky one. When you're looking at investments, they always give you annual interest, but money is not compounded annually. It's generally and almost everything compounded
Quarterly.
credit cards, mortgage, daily.
Daily.
Yeah. You might only pay it once a month, but you're compounded daily. That's why if you pay it early, if you're paying off your credit card, it doesn't matter. If you have a balance on your credit card and you send a payment in early, you pay less interest. So if you send your mortgage payment, all accounts of that nature, and by the way, all investments are daily, not monthly. You might get the monthly statement, but it's still compounded daily. So if you don't have to wait till the end of the month to pull the money out, in other words. So that's periodic growth. But do people grow periodically? That's not true. You know why? You all have different birthdays. You were all born at different times of the day. Oh my gosh. If we had a monitor on the wall there that had the population growth, or population, of planet Earth, the ones would be going so fast we can't see it, and the tens would be going really fast. The hundreds are probably moving. Even the thousands have changed since this class has started, hasn't it? Because it's constant, it's continuous, it never stops. So we say that the rate of change of growth of any population, that's the instantaneous rate of change, not the average rate. When you're in your car and you're driving from point A to point B, if I take how far you traveled and I take how long it took you, I can tell you your average speed. But what if I said, how fast were you going right at that moment when you passed that marker? That's your instantaneous rate of change. That's a derivative automatically. So this is the instantaneous rate of change of population with respect to time. It has to be a constant multiple of the population. Think of K like your percent. So if I said a population is growing 3% per year, then K is 0.03. What if K is negative?
Population decline.
Right, or in general we call that decay, right? So growth is if K is positive, decay is when K is negative. You don't put a negative in front of that, you calculate the value of K. Now if it's growth, you already know K is positive. If it's decay, you know K is going to be negative. So if I said, how long will it take for my population to double, that's a value. If it's decay, what's the follow-up, the similar question? When will there be half as much? That's called half-life. That's the same as doubling time. Half-life and doubling time are exactly the same. One's growing, one's decaying. It's the same thing. You're going to get the same number, okay, but depending which way you're going. Now, this is the universal equation that governs population growth. Now, I want to solve this. I have one independent variable, one dependent variable. That means all integrations must be done with respect to t. Hey, wait a minute. Didn't we just do this problem? Isn't this a separable differential equation?
Yeah.
So can I do it as 1 over y dy dt equals k, which basically means I'm going to, everybody see that? When we say separable, it has the feel that I am pulling the derivative apart. I am not, but in the end, notationally, that's what it looks like. Because I just integrated dy dt with respect to t, that makes it dy, and the other side I integrated with respect to t. It feels like I just simply pulled it apart. Mathematically, you're not, but notationally, you are. Because again, you're not pulling it apart because it's not a quotient.
Is there any point where that distinction would trip us up if we were just thinking of it as multiplying the dt to the other side?
Well, because if I'm not careful, I could flip the order of make it dt dy, which would not be the same problem. If I'm treating these as values, see, couldn't I then just come back and put the dy over here if I'm thinking of it that way? And that would not be the same thing because now I've switched which one's dependent and independent, which, again, all hell breaks loose. The dogs and cats thing still trouble me every time, we have a dog and she's afraid of cats right now. So what do I do now? Well, this is pretty easy. What's the antiderivative of 1 over y dy?
Natural log of the absolute.
Good. And the other side would be kt, we'll call it c1. Now, if y represents population, can y be negative?
No.
No. So can I ignore the absolute value in this case? Yes. In general, yes, it is absolute value. specifically in this case, since it cannot be negative, the rule of thumb, even in Calc 1 when you first learned it, you always put the absolute value, but then when you looked at the function that was there, you know, if what was there was x squared plus 5, you drop the absolute value because that's a strictly positive quantity. It's never wrong to leave the absolute value in there. But it makes the next step kind of tricky because I need to write y equals, which means I need to exponentiate both sides. So I don't want an absolute value. I want that. Okay? Rules of exponents, can I write it like this? Now, many of you have seen this before because I do this in Calc. Heck, I did this morning in Calc 2. This is early Calc 2. This is not even advanced stuff, but it is the precursor for all the stuff we're going to be doing, which is why I'm doing it again. Yeah, it is in the book. I'm not just throwing it in as review. And it also is stuff that nobody's done recently. So I don't care how good you are at Calc 2. You didn't do Calc 2 last semester, I don't think. So there's some rust. So we want to make sure. If C1 can represent any real number, then e to the C1 is also arbitrary. Can e to the C, we'll call it C2. Can e to the C1 be any real number?
Yeah.
Are you sure? E to the C1?
Yeah, it could be any number.
Can e to the C1 be 0?
No.
Can it be
unless-
negative?
No.
No, it's strictly positive. It can be any positive. C1 can be any real number including 0, positive or negative. But e to the C1 is strictly positive, and that's a good thing. Because otherwise I might have negative population at some point, and that would be bad. Everybody understand what I just said? Oh.
So it's important to put that C2 cannot be 0.
Well, we'll figure out in a moment because we can. Right now, it looks like we have a bunch of arbitrary constants. K is not an arbitrary constant. K, I have to know. K, there's two ways to find K. I told you that the town is growing at this %, or I measure what is today's population, pick some fixed point in the future. What is the population? And now calculating K is trivial. It actually is. You learned to do that, believe it or not, in remedial algebra. If I tell you the initial population, then you give me K, I can tell you exactly what I can expect in the future in that case. But C2 seems totally arbitrary. Y of 0, that would be now. That would be, I'm starting the count today. That's called my initial condition, and we usually indicate it with a subscript of 0. Most of you are familiar with this in your science classes, right? A subscript of 0 means evaluated now, at time 0. What does this equal? Well, let's see, it would be C2 e to the,
0.
wait a minute, C2 is not an arbitrary constant at all.
It's the initial.
It's the initial population. Oh, which gives us the universal equation that we all use. This is how all populations grow. Not because I told you, this is why we know populations grow exponentially, because we just solved a simple differential equation. And what's even cooler is the initial population shows up right here. Now, this is the only one I'm going to solve of this. The other ones I just want to be able to state what the answer is. Okay, I'm okay with just stating. But how many, by the way, be honest, how many have seen what I just did before? You know, in my class, you better raise your hand. But, you know, I don't expect that you remember it. But I want it to make perfect sense. Because we have to use this mathematics and at a higher and higher level constantly now. We just solved a very simple separable differential equation. Now, I didn't use that term today when I did my Calc 2 class. They're going to do separable next day. I went through and explained the whole u sub thing, and when you're integrating du dx with respect to x, that's why it's the integral of du. That's why we write du equals something dx. It's not that I'm pulling things apart. It's from a notation. It's very confusing if you're not really, really on top of things. So what kind of questions can I ask? I would know y0. That's not a calculation. I either am told k or I can calculate k. How do I calculate k? Well, if I know y0 today, and I say, okay, then what's the population? Give me a fixed interval of time. I give you that population, and now I can work back and solve, because I have the value of t. Right? I have a value for the y, I have a value for t, and then I solve for k. So, I'll give you a simple question. All right? You and I are both going to invest our money in the same account. We found this huge interest-earning account. I only have $1, though. He's got $1 million. He did well last year with his Bitcoin. He sold Bitcoin right at the right time. Okay. Whose money's going to double first?
At the same time.
I'm only putting in $1. He's putting in $1 million. Same accounts.
Should be the same rate.
You guys are thinking way too much. Whose money's going to double first?
his.
It is a trick question.
No, they should double at the same time.
They should double at the exact same
They will
time.
eventually.
Now, who's gonna reach $2 million first? He is, okay. When will my population double? You understand that that's the question I'm asking?
Yeah.
All right, so let's solve it. So 2y0 is going to equal y0 e to the kt, and the first step is to,
Divide everything by y0.
so wait a minute, how long it takes me to double is completely independent of my starting population? How long does it take my money to double is going to be completely independent on how much I put in the bank? Yes. How much money I'm going to have in the end depends on how much money I put in, not how long it takes to double. That's why I said it's a trick question. We all were thinking about, well, you only have $1. It should be way easier for you to double your money. So I now have 2 equals e to the kt. So the log 2 equals kt. And this is a universal equation that I guarantee everybody here did in remedial algebra about 1 million years ago. So t equals log 2 over k. This is the universal doubling time for continuous growth. What if I want to triple?
Then 3.
Log 3, yeah, that's easy. Now, I have a population. It turns out I have a town and nobody's moving into my town. Nobody likes it here. In fact, you can't leave either. The only way you can leave is to die, yeah. So we are losing people over time. Is that possible? Yeah, we're gonna be a ghost town eventually. In this case, my k would be negative. So instead of asking how long it will take the population to double, I'm going to ask you how long will it take my population to have half as many? What's the answer?
Negative.
Ln upon half over k.
Same answer. Except because k is negative, you just put a negative here. The half-life and the doubling are exactly the same. Think of it this way. If I'm doubling, I'm saying how long will it take me to double? If it's half-life, how long ago was there twice as much? You see why it's the same question? How long ago? So this is something, again, people did a long time ago, and he's like, oh yeah, I forgot about that. But I have fun because I remember my kids were in school and they'd always have that question. Some of you remember this one. The population of India is this, the population of China is this, India is growing at this rate, China's growing at this rate. When will India catch China and pass them up? You guys remember that question? It's in all the social studies books. But again, they're using that year as if that year it's staying constant for the whole year. Now here's the problem that I have with all these kind of problems. How long is it going to take our population to double? It's going to take this long. When will the population of San Diego reach a certain number and you tell me exactly when it is? What will the population be in San Diego in 2030 and you tell me?
No.
If you know that answer, what's going to be the score of the Super Bowl in a couple weeks? Because I can make a lot of money. Because if you know what the population is going to be in the future, then you already know the Super Bowl score because you went to Back to the Future and did a whole thing. And you know, did you talk to your former self and all that stuff? I can't remember how that works. That's not possible to tell me what the population is going to be in the future. But all the books, every algebra book, that's how they ask the question, no. And first of all, is that population going to grow at that rate for eternity?
No.
You remember this question? You got the bacteria in the petri dish and it doubles every 4 hours? And then it's going to keep doubling and doubling and doubling. Eventually, it's going to break through. It's going to cover the floor. It's going to cover the wall. All of us are going to get eaten alive by these bacteria. Or what's the other possible outcome?
They just die.
They're all dead because
They don't make
Too
that.
many.
there's 2 things.
There's not enough
Overpopulation.
resources.
Resource, yeah. Room and resources. They run out of food and they run out of room and they all die. In other words, it's finite. All population growth problems, your growth rate is finite. It's impossible. Both logically and mathematically, it's impossible for that to carry out forever. You would always run out of room. This planet is not infinite. You can't have population grow forever at that rate. But can it grow for a finite period of time at that rate? Yeah, it always will. If I said growing up for 6 months, for a year, for 5 years, it's growing at a particular rate. So the way we ask the question is, over the last however many years, the population of San Diego has grown at this rate. If it continues at that rate, what will the population be next year, 5 years, 10 years? That's the only way you can ask that question that have it make any sense. Now, whatever number I get, is it going to be right? Is it going to rain tomorrow based on last week's forecast? No, but it's the highest probability outcome based on what we knew last week. Did they change it already this week? Probably. But based on what I know from the past, it's the best starting point to do the future, because that's how all cities plan. That's how you plan infrastructure, based on what you believe is probably the case. You can't say the population is going to be this, because that means you're predicting the future. But that's how we always did the math, if it continues at that rate. Now, are there things where we actually can do this? Where we actually can see? Yeah, think of like a crystal. Anybody ever seen a crystal that's growing? It's real cool, it's just growing. And that will stay at that growth rate for a very long period of time. It won't be forever. How about when things die? Short of some external force acting on it, the decay rate's going to be constant. Literally, there's nothing left unless something acts upon it along the way. So there are certain things that, yeah, it actually makes perfect sense to do it that way. Okay? Now, one of the most important applications that I like doing, and we're not going to solve this problem until, like I said, we get to chapter 3, but I want to state it because it's a version of this. And I do this problem in Cal 2, and I did this problem today. All right. I have a hot cup of coffee. I'm going to set it on the table. Now, I'm going to make one assumption and one assumption only. We're going to close the room up so that we can keep the room temperature constant. That is actually an absolute criteria in order to do this. By the way, is that an unreasonable criteria that you're in a constant room temperature environment in any situation? And mild changes aren't going to make much difference. But I can't be outside, day and night, wild changes. So I set the hot cup of coffee down. What immediately starts to happen? I asked this question this morning, and one of the students said, well, because of the heat exchange, that spot on the table is going to start getting warmer. I went, it's really not where I was going with it. I just started laughing, like, the heat exchange, the table's going to get warmer. Not the cup of coffee's going to get cooler, but the table's going to get warmer.
It's going to heat the room.
It's going to heat up the room's getting warmer. So the cup of coffee's going to start getting cooler. And it's going to keep cooling down, it's going to keep cooling down. So let me draw a picture of this. My goodness, why is it? Both of my black pens. Oh, is this a good one? Hold on. Oh, that one's still good. Okay. I don't know why I keep grabbing the wrong pens. These are all brand new. All right. So that's time. We'll usually use little t. That's temperature. We'll usually use a big T. This is the room temperature. We usually use A for ambient. It's the ambient temperature. That's constant. That's known. I have a hot cup of coffee. At time 0, I'm right here. Now, the coffee starts cooling down. So it's going to keep cooling down, keep cooling down. Eventually, room temperature is going to keep going. Wait a minute. It's going to get colder and colder. It's eventually going to freeze. It's going to keep getting colder. It's going to approach absolute 0, in which case all molecular movement stops. The ice ball starts spreading out, and next thing you know, planet Earth, we're floating ice ball. We're all dead. Because I left a cup of coffee. Oh, man, I hate it when that happens. Or not. What part of this is flawed?
I don't think it's linear.
Well, actually, it's simpler than that.
It's
Can't reach room temperature.
It'll stop.
It's not possible to reach room temperature. Oh, so it gets so now then goes sideways, right? No, because this is going to be a differential equation, so it has to be differentiable, and that would be can't have a jagged edge. One other possibility, and that is, when does it reach room temperature?
Never.
Never.
Yeah.
It's asymptotic. It actually can't reach room temperature. That's absolute impossible. Now, when you're measuring temperature with a cheap thermometer, it's not going to take very long before your readings are going to be the same, but they might not be the same, 10 decimal places out. No, you're never going to reach room temperature, but you're going to be so close it doesn't matter. So it's asymptotic. That's the key. I always have fun with that. It doesn't pass through. This is one of my favorite questions. Let's assume for a moment that water does freeze at exactly 32 degrees. I mean, I don't know if it does or not. It's probably a little bit off, but let's just say it does at 32. So of course you are going to host a Super Bowl party. You got to make sure you have lots of ice for all those soft drinks that you're going to be serving your friends. And so you put all these ice trays in the freezer days ahead of time. And so the day of the game, you go to pull out all your ice trays. What are you going to find?
Ice.
There's no ice. Not one of them's frozen. That's not possible. Why? They can only approach 32 degrees. It's not actually possible for them to be 32 degrees. Infinity, yes. If I take the limit as time approaches infinity. So that's why nobody sets their freezer at 32 degrees. You set it at like 20. I'm gonna turn the heat on the stove to exactly 212 degrees, and now I'm gonna bring my water to a boil. Guess what? It's never gonna boil. Gotta go a little hotter than that. It's approaching, that's an asymptote. It can't reach it, it can only approach it. You think I'm joking with you? No, that's simple physics.
Yeah.
Yeah, you gotta go a little colder or a little hotter to what you wanna get to. So, how do I model an equation? Well, when does this thing cool the fastest?
It's the hottest.
At the beginning, when it's got the greatest difference. When is it really going slow? When I get to here and I wait 5 minutes, I might not notice a change. That is the worst. Anybody drink coffee here on a regular basis? And you set your mug down for a little while and you come back to it and you go, oh God, it's lukewarm. By the way, it's gonna be lukewarm for the rest of the day. It's gonna stay that way forever because it's so close to room temperature now, it's not gonna matter. That's why I'll pop my coffee back in the microwave and make it hot again. So, how do I model this differential equation? What is the rate of change of the temperature with respect to time? At any given moment, this is exactly the same as the population growth, only a little more on steroids. What is determining the rate?
The inverse.
The difference between the cup of coffee and the room temperature. And you just said the greatest is when the difference is big, the smallest is when the difference is small. So there's still a constant. I don't know what the constant is, but it's the constant. A is a constant. A is known. But T minus A starts really large. K is a constant. We're going to calculate K later on, not today. K is a constant. Whatever K is, K is. Is K going to be positive or negative?
Negative.
Yeah, because I'm cooling down. When this difference is big, this rate of change is large. When this difference is small, this rate of change is small. And think of the rate of change, if it helps, is the slope of the tangent line at every point. That's exactly what it. Now, we are not going to solve this today. I just want you to state this today. The solving of this we're going to do on another day, and it's not that hard. It's not that much different from that one. This is called Newton's law of cooling. Now, I do a lot of cooking at my house, and I go through a lot of chicken. Got a lot of chicken in the freezer. And I'm not joking. So today, when I get home, maybe I'm going to take some frozen chicken out and I'm going to put it on the counter. My kitchen stays pretty constant room temperature. What's going to happen to that chicken? It's going to start warming up. Uh-oh, and it's going to get warmer and warmer and warmer, and eventually it's going to burst into flames. In fact, it's going to get so hot it's going to go supernova and burn up all the oxygen in the air, in which case it's going to be a big ball of fire. Or is it actually the same thing in reverse?
It's the same.
In other words, is it just this? Yeah. It's called Newton's law of cooling, but it applies to the heating as well. It's the same thing. The room temperature is an asymptote. That's where it would approach. Now, I don't want to go into too many of the applications of this because we're not actually solving the problem. But this is one of the most applied things that we actually use in real life.
Oh, we can't get to absolute zero.
Say again?
We can't get to absolute zero for this reason.
You can't get to absolute zero if...
For that same reason.
Oh, right. yeah. It's a limit, but I don't think we can even come close to it, even if we wanted to. Now, this turns out, we're going to solve this because this is a differential equations course. We want to learn how to solve differential equations. This turns out to be one of the most useful ones, and I'm going to give you a little insight because the class you're in now. Some of you will be taking a class in partial differential equations. I took one, and I took it over an intersection. That was gnarly when I was in college. But one of the problems that we looked at, and I think is a very valid problem, look at the tabletop. Okay, the tabletop is your barbecue. Does anyone here ever grill? Barbecue at home. And of course, as you know, every single point on the surface of your barbecue is exactly the same temp at all times, right? I'm winking at you, so you know. No, you have hot spots, you have cold spots. In fact, would it be safer to say there's no 2 points that are ever the exact same temperature, no matter how much you spent on that grill? No. So what you have are heat signatures, heat trails that are left behind. There is a function that exists. I don't know what it is. I'll let you figure it out. But there's a function that exists that will describe what the temperature is at every point on the surface. It's two-dimensional at this point. So at every x and y, you'll have a temperature. But that means if I'm heating or cooling, my temperature is going to constantly be changing. So there is a differential equation. It's a partial differential equation. It's very complicated. We are not going to talk about that. That is a much higher level of math, but that is what's actually used in real life.
The grill is too complicated.
Well, the reverse, the differential equation that we get based on what are called heat signatures. Now, I'm going to give you a simple example of one, okay? When there is a fire in any building, you know, the insurance company will come in. There's only two causes of a fire, and they both begin with A. Accident and arson. I know you've heard this before. So what the insurance companies do, and by the way, I always laugh about this. People don't understand insurance in general. Are there any homeowners here? Anybody? Nobody here owns a home? Paying a mortgage? Okay. You might be able to cheat death. You might be able to cheat taxes, but there's one thing that you cannot do. You cannot own a home in the United States and not have fire insurance. That is not something, it's not even possible. If you decided to let your fire insurance lapse and not pay it, the bank just takes your house away. There's nothing you can do. No, you have to have fire insurance. You don't have to eat, but you have to have fire insurance because the replacement of your house, and because the bank owns your house until you paid it off, which most people never do. So insurance companies are the wealthiest things on planet Earth. It's not even close. If I have life insurance, my wife has life insurance, if every American who has life insurance died today, life insurance companies could pay off the policies, which I've heard measure in the quadrillions. Insurance companies are worth significantly more than entire countries. It's not even close, which is why insurance is outside the law. And I don't mean that illegal. I'm not going to ask because that's a touchy subject, but if anybody here was left a life insurance policy because somebody died, it cannot be touched. Your life insurance policy cannot be, or life insurance benefits cannot be taxed, they cannot be touched. Nobody can know except you. Any insurance settlement cannot be touched in any way by any government. They are completely outside of government control because of the sheer magnitude and power and value. Insurance is, so in other words, when that insurance company comes in to determine, oh, they're good. They know their math. Whenever there's a fire, now it's three-dimensional, but let's think of the floor if it helps. There will be heat signatures left behind. And I've read about this years ago. This is fascinating science. You can find the exact point in space or on the floor exactly where the fire occurred. So when they work backwards and there's lots of equipment that they will use. I don't know, I think it's the same stuff they use in Ghostbusters, you know, the spectral equipment, and I don't know. But you know, they find that spot on the wall and they see all the frayed wires and burnt out stuff. They you know, obviously everything was really old, caught fire here. One of the coolest things I ever read though, they found almost down to the atomic level. I mean, you couldn't see it. They found remnants of the gas-soaked rag, not visible to the naked eye because it was so small. But the equipment found, people went to jail.
Oh my God.
They went to jail because it was hundreds of millions of dollars, arson, fraud. By the way, insurance fraud. You're probably better off just killing somebody, you know. Insurance fraud, oh my gosh. I had somebody get in an accident with me one time, they were in the military, and we made a police report. It was entirely his fault, he felt really terrible, but his wife was just yelling at him the whole time and screaming. This was on a Saturday. On Monday, the insurance company calls me and says, he changed his story. He says, that's really unfortunate, because you guys already made a police report. He had been in the service for over 20 years. He was discharged dishonorably that day. His entire retirement, done. You don't do that in the military. But because the insurance didn't pay him anything, they decided not to prosecute for insurance fraud. But he changed his story after he made a police report. And said it's 100% my fault. And he came up with a new story that violates laws of physics. He T-boned my car, and he said, no, we were driving side by side, and we just kind of bounced off each other. Yeah, but the thing is, so it turns out to be one of the most powerful things that insurance uses is exactly a three-dimensional version of this. It's much harder. But I have many other case examples that I'll do on another day. It's cool stuff because it only uses math that we know right now. Okay. Now, the last one that I want to look at today, this one is often called the spread of a rumor problem. I like the spread of a rumor problem because there's another name for it. It's the mathematical model for the spread of a disease, but I like to use it as the spread of a rumor. And the interesting thing is that when I was teaching this in a DiffyQ class, something had come out on the news that day. I think it was during the pandemic and stuff. It was crazy. I think it was like almost literally right when we we were doing this right when, the whole COVID thing was starting, and we were talking about how does this spread. It was part of the lecture, the mathematics. Now, we are in an enclosed environment. I like using a stadium. I like using a place where there's lots of people. Okay, so we're in a stadium. We're all going to the Super Bowl. Okay, I got tickets for everybody. I wrote them out myself. I don't know if they're going to be on. Do they take crayon? I don't know. So I have tickets. We're all going to the Super Bowl. There's going to be 60,000 people there, and then they're going to shut the doors. Now, I have this rumor that I just can't keep to myself. So I tell you. And you can't keep it to yourself, and so we tell these guys, and you guys can't keep it, so tell these guys. There's a mathematical model that describes how this works. All you have to have is the beginning. That says at any given moment how many people will know the rumor. Now, when there's 60,000 people in the stadium, and I walk in, nobody knows it but me. What's going to happen early on? It's going to spread like wildfire, isn't it? Now, most everybody in the stadium's heard the rumor. What's going to happen? It's got to slow down because there's not very many people left who haven't heard the rumor yet. So the rate of spread, if you want to call it, is dependent on two things: how many people know, and how many people don't know. When do you think the spread will be at its absolute peak?
The beginning.
When exactly half. Exactly. Good. When exactly half. It's going to speed up, and exactly half it'll start slowing down. This is what the CDC actually uses. And I will give you one example. Has anybody ever seen the movie Outbreak? Dustin Hoffman and Renee Russo, is that her name? It's maybe the scariest movie I've ever seen because it's real. I think it was like late 90s. It's a monkey. It starts off there in Africa, and they literally nuke an entire village because the Ebola virus had spread there, and because we can't have it spread. And somehow this little monkey escapes, and somebody brings it back to the U.S., but the monkey has the virus. And the guy gets it, and the scene where they're in the theater, that was so creepy. And he coughs. He's coughing. You can see the germs in the air. And within hours, everybody in the theater, and people are dying left and right. And it's starting to spread. And the military comes in and they get involved and they send all their experts. And they can't make an antidote without the monkey. They do find the monkey, by the way. But that's not the scary part. The scary part is they show a map of the United States. It shows the region in the United States, like within 48 hours. They've modeled it exponentially with the exact formula we're going to learn. With the entire United States within 48 hours. And so the military goes in there to nuke the American town. That's why I say it's so scary. I've talked to people in the military higher up, and they said that's exactly what would happen. You have an infectious disease that's going to kill everybody. They would go on and nuke it. Now, the reason that's so terrifying is when COVID first hit, we didn't know what was going on. But COVID was not one community only. It was all over the world. This is one small community, and it started to spread. So, but the point is the mathematics that we use is exactly the same as the mathematics they use in this movie. They don't show you that, but I know that.
They do that for poultry and chickens. When there's a virus, they kill all the poultry and the.
I think you don't have a choice, do you?
Yeah.
You can't have a favorite rooster, but I'll let him go. So the formula, let's say there are N people, and there are X know the rumor. We'll use rumor because it's so much happier. How many people don't know the rumor? N minus X. Now, these are the people in the stadium. I walk into the stadium. I'm not one of those. You with me on that one? So how many actually are there altogether? If there's N people in the stadium and I walk in, now there's N plus 1 people. I've told a bunch of people, so X people, but really it's what? Plus 1, plus 1. Now it's not life and death if you forget the plus 1, but it's a tiny, tiny, tiny change in the math at the end. So there's a stadium of 60,000 people and none of them know it. I know it. So I am the one person who knows the rumor. As I start telling people, X more people are going to know the rumor, N minus X people are not going to know the rumor. But in actuality, it's always going to be one more person Because otherwise I'm not counting. Does everybody see that? So what is the rate of change? Let's call, it's the rate of change of the number of people who know the rumor. So x would be our variable, wouldn't it? So it'd be dx dt will be a constant multiple of what? That times that. So the reason it has to be +1 is when we first start the problem, does anybody else in the stadium know the rumor?
No.
No, but I know the rumor. So x is 0, but there's still one person who knows the rumor. And then this is their 60,000 right here. You see what happens? Now, like Benito said, as the more and more people know and less people don't know, these numbers get closer together. Now, how do you know that? I want you to think really simple. Just take the numbers, the integers 1 through 10. Okay, 0 times 10, 1 times 9, 2 times 8, 3 times 7, 4 times 6, 5 times 5. What's the biggest product?
5 times.
Is it going to be 5 times 5? It's exactly the same thing, isn't it? Oh, I have number and 10 minus number, and I'm multiplying them together. Okay, when is it going to be the biggest? When they're the same number. So when is this rate of change going to be highest? When these numbers are exactly the same, or close to being the same. So this is the differential equation that governs the spread of a rumor.
Contagion.
Does it govern the spread of a disease in general?
No, because some people may be resistant.
No, it's actually, there's a simpler reason than that. Because we're spread out, yeah. I'm in an enclosed environment. Nobody's coming, nobody's going. So that's why this doesn't work for COVID. Because people were traveling, they were taking it with them, okay? You guys understand that? This is in an enclosed environment. So is this artificial? Yes, but do we use it now as a starting point? So in the movie I was talking about Outbreak, it was a town where nobody was allowed to go or come. Yeah. So in other words, it really was an enclosed environment in that sort. So that's why they could do this. But the problem was they said if people leave, then they modeled the spread based on people leaving. Do you remember, let's see, COVID started March 11th, which was a Wednesday, 2020, the day the world stood still, I always call it. Not that fall, or was it that fall? Maybe it was that fall. Remember, people started going back to school. All the universities started letting everyone back. And then within a week or two, do you remember they all sent everyone home again because everyone had COVID? You know, remember San Diego State, they were having frat parties left and right, and they were finding hundreds of people at a time were testing positive. Brilliant. But the idiot thing that they all did, they sent everyone home. You have an infectious disease? Hey, I'm just going to send you across the country to where you're from. Dumbest thing imaginable. Now, the school my son went to, and I know USD did the same thing, you know what they did? They quarantined on campus. They didn't let anybody leave. And therefore, nobody took COVID with them and spread it anywhere else. They quarantined on campus till they were ready, and they kept going. A few schools figured that one out, that, you know what, why would you send the disease home? That made no sense. But that's what most universities did, and then they closed it a week or two later. Major universities were closed 2 weeks after the start of this because they didn't have a contingency. They didn't have a way of dealing with that. Okay. But you're actually going to learn math.